In this recording, we're going to start looking at a third example of trying to find a quotient group. And we're going to let G be S4 again, but this time we're going to let H be the alternating group for S4. That is the set of even permutations in S4. And it turns out that A4 has two. So A4 has two left cosets. The first one is just A4 itself, which is E times A4. And the second one is any odd permutation. Let's see, I'm just going to take 1 goes to 2 times A4. And this actually is the same as alpha times A4, where alpha is any odd permutation. And the first thing that I want to do is I want to show why these are the only two left cosets. So let's look at that. Why is this so? Well, one thing that I want to recall is I want to recall that two left cosets are equal if and only if one of them's inverse times the other one belongs to the subset. And what I want to realize is this. If alpha and beta are both even, then clearly alpha inverse times beta, well, that's an even permutation times another even permutation. That is an even permutation, so it belongs to A4. So one coset for A4 consists of all the even permutations. And of course, that happens to just be A4 itself, which is E times A4, because E itself is an even permutation. Because the inversion number of E turned out to be 0. Well, let's see. The other case is if alpha and beta are both odd permutations, then what we happen to have when we look at alpha inverse times beta, that's going to be another odd permutation times an odd permutation. And an odd permutation times an odd permutation is an even permutation. And so alpha inverse times beta is indeed inside A4. And what this means is that we get one coset for A4 consisting of all of the odd permutations. Well, what this means is that we can now define an operation on the set of two left cosets, and we can make it into a group. So let's see how that looks. S4 mod A4 is going to consist of two groups. The first one I'm going to call E, and the second one I'm going to call O, and where E is equal to A4, and that's the set of even permutations, and O is any odd permutation times A4, and that's just all of the odds. And for any alpha and beta inside of S4, we're going to define this particular coset, O times with this particular coset, is just going to be uh, is going to be alpha beta times A4. And we have to basically show that this particular operation is a group operation. Well, the very first thing that we need to do is we need to look at, is this operation well defined? And it turns out that it's not too hard to show that this is well defined. There are basically 4 cases that we have to deal with. And the first case is going to be alpha is even, beta is even. Well, in this case, alpha beta is also even, and that's going to imply that we have alpha beta times A4 will be A4, which is, of course, the set of evens. And it doesn't really matter what name for alpha or beta I pick as long as they're both even. Well, the second case is going to be alpha is even and beta is odd. And in this case, what we're going to wind up having is that alpha times beta times A4 is going to be an even permutation times an odd permutation times A4, and that's just going to be an odd permutation times A4, and every odd permutation's left coset is the same as the left coset defined by 1 goes to 2 times A4, and that's just the set of odd permutations. Well, the next case is very similar. If we have alpha is an odd permutation, beta is an even permutation, the same kind of thing happens. Alpha beta times A4 is going to be an odd permutation times an even permutation times A4, and that again will be some odd permutation times A4, but every odd permutation has the same left coset for A4. That's the set of odd permutations, or the set that is represented by 1 goes to 2 times A4. And then the fourth case that we have to deal with is alpha and beta are both even. But if I look at the 2 cosets, if I basically look at this situation, then alpha times beta times A4 is always going to be an even permutation times an even permutation times A4. Well, that's going to be another even permutation times A4, and that's going to be the set of even permutations, which is just A4. Essentially, what this means is that we've got a group multiplication table, so to speak, that looks like this. So the multiplication table for our multiplication table for this structure is going to look like this. We are going to have our O times, and we've got A4, and we've got the other left coset, and we have A4, and we have the other left coset. Well, this one's just going to be A4 because we've already seen if alpha and beta are both in A4, then the way we've defined this product turns out to just be A4. And if we have if we have alpha in A4 and beta in the other right coset, we've already seen that this particular product is just going to be the group of odd permutations. So this is just going to be this guy again. And let's see. So this is case 1. Case 1. This was case 2. That's case 2. Let's see. If we look at this box, we're going to want alpha to be in the odd set, and beta is going to be in the even set. And when we do that, alpha beta times A4 turned out to be all of the odd cases. So this winds up being 1, 2, A4 again. And so this was 3. And this final box was when alpha was an odd permutation and beta was an odd permutation. And we found out that when we looked at alpha beta times A4, that turned out to be the set of not the set of odds, that turned out to be the set of evens, or A4 again. And so we have a multiplication table that looks like this. And that multiplication table looks suspiciously like a multiplication table that we have seen for a different group. So let's continue on. We have the multiplication table for S4 modded with A4 that looked like this. And A4 was A4, O times A4 was A4. A4 O times 1 comma 2A was 1 comma 2A. And let's see. Let's just get rid of that straight mark. Yeah, that should be an A4. And 1 comma 2A4 times A4 was 1 comma 2A4. And this one, O times with that one, turned out to be A4 again. Well, I want to think about the addition table for Z2 under its addition. Well, that table, that table looks like this. 0, 1, 0, 1. And when I look at 0 plus 0 mod 2, I get 0. When I look at 0 plus 1 mod 2, I get 1. When I look at 1 plus 0 mod 2, I get 1. And when I look at 1 plus 1 mod 2, I get 0. Now, what I want to notice is that structurally, these two tables seem the same. They have the same structure. In other words, if I make a function going from S4 to A4 into Z2 given by f of A4 is equal to 0 and f of 1 goes to 2 times A4 is equal to 1, then this table here, this table up here, gets rewritten as this table here. And we can see that by simply writing on top of one of the tables. This 0 is f of A4. This 1 is f of 1 comma 2 times A4. This one is f of 1 comma 2 times A4, and this particular 0 is f of A4. Well, since they have the same structure, and this particular function is clearly one-to-one and onto, and this stuff here says f preserves the group operation, what we know is that S4 divided by A4 is indeed isomorphic to Z2 under plus. And that's enough to say that S4 mod A4 is indeed a group. In fact, if we get rid of this mark that we no longer need, we can even go as far as saying that S4 mod A4 is an abelian group. Now, the importance of this example is that it means that in that previous video, the problem in the previous video is not as simple as S4 is not commutative. The problem in that second video is more subtle. And we will look at that subtlety in the next video.